What's going on, my friends? Welcome back to the show. And then this is the final one of the series. And this one specifically, we're going to be continuing where we left off in the last one. And this last discussion involves this bottom up approach of these knapsack dynamic or slash greedy programming problem. So in this case, we basically just gonna run down as to how this bottomed up approach was actually gotten into using the previous two ones. The previous ones I'm talking about this very basic one here, basic recursion, and then this recursion with memo. So basically, if we take a look here, so this is, before I even get there, let me just clarify something. If in an interview or even in a dynamic programming contest or something like that, if you come up with this solution here with the memo, I think that is very much acceptable. I think you'll be off, should be done. There shouldn't be too much concern about this one here. But if you do have a chance, or if maybe they are too strict into what they want, then you can consider this solution here. But this is more a bit of an overkill to some degree. It really depends on your application. For a lot of applications, this solution here with the memo would be sufficiently enough. As you can see here from our previous one, you see the computation time. There isn't that much of a difference of a performance gain from implementing this one here. So with that out of the way, let's get down to details of it. So the same thing applies here. This one here takes two arguments. The first argument is our objects which we either include or exclude, and we cannot take a fraction of. These objects have a value and a weight. And then over here we have W, which is our knapsack capacity. And then you have a base case here. If our knapsack has a capacity of 0, then we really cannot do anything. We return 0. And then if the items that we are picking have a count of 0 or less, then we really cannot pick anything. That's why we return a 0 here. Otherwise, if there is an item and we have a capacity to take them, then the first thing we do is we build our memo. It doesn't necessarily have to be called a memo. It could be called anything. You can call it a table. Sometimes this thing is called a tabulation method. So this is more or less a table. It's a two-dimensional array, as you can see here. We initialize it with 0, and it has a row and height of row and column. This here is the rows, and this here is the number of columns, which are n+1. And then as you can see here, we start computing from the first element, which is 1, simply because we do need the previous element in our computation. As you can see here, we have -1. And then basically what happens in here, we first consider one item at a time, using this for loop here, and this runs in an order of n times w, magnitude of n times w, which is less than exponential time, less than quadratic time. You have that. Once you have that, now you pick your items one at a time. You start off with the very first one at element at index 0, which is the first one that will be taken during the first iteration. And we're taking it from the list over here, and as you can see, now we consider its weight. And then we check if these item can fit inside of our subdivision of this total capacity. If it can fit, then we add it to the memo, and if it doesn't fit, we leave it. And then we see what happens if we increase the weight. Is it possible for us to include? Just like that. So basically, once you have that, basically you then realize that these values here, the structure of this is similar to the structure of these ones here. So let me just collapse this a little bit just so I can give some real estate. And then you see here, so these, by taking an item, this is essentially the same, similar to some degree, or the structure is the same. So you compare an item to a weight, and this is the action of taking an item is this action here, which is item weight plus some previously computed value, which is a similar thing here as items weight times, plus some previously computed value. In this case of this recursive, it wouldn't be previously computed, it would be calculated on the fly. But you have a similar notation here. You're saying our memo at the index of the current value minus item weight. That's why you need that condition to say your item weight is less than your weight. Otherwise, you'll have a null pointer reference, array index out of bound. And then just basically how it is. And to compute it in the same way as the previous one, and then you simply take an item. If you take the item, you just chuck it in there, and then the action of leaving an item comprises of these value here, which is similar to the value here. So here we subtract one item from the list, and the capacity stays the same. And this is the similar thing here. The capacity stays the same, but we consider the previous value. And then that's pretty much it. And then at the end we compute the largest value here. And then once you're done with that you will then have your solution, and that's pretty much it. And in future we can talk about, just let me know in the comments below if you guys need me to get into further details or like code this thing from scratch with you. Let me know in the comments below. I can definitely do that for you guys, and I can code all this thing from scratch. But like I said before, it'll be significantly difficult to come up with this from scratch. You would need to have coded these two ones here before. So let me know, and then we can take it from there. Otherwise, let's just run through the execution times and see how much they differ. We already have them here, but for the sake of this, let's just change it. Let's just change one of values. Let's just delete 2 or 3 values here. In fact, let's not delete. Let's make them more. Let's make them more. So change this maybe to that 55. Just like that. And our capacity, let's just say our capacity is 1500 this time. And then let's give it a bash. This is that function we're interested in, as this one here. And as you can see, all these functions, I'm passing them the same value that I want. The options, which are these values here, values in this array. And then you see our capacity, I just redefined it to be 1005. So now let's just see how quick this thing is. And then this basically marks the end of our computation of the Knapsack dynamic programming solution. And if any of you stayed this long, you really are interested in this, and I would like to get some feedback on you as to what detail, to what extent would you like me to break this thing down to. I can do that for you, and without any troubles whatsoever. Just let me know. As you can see, this thing is taking a little bit longer to compute, but it is what it is. We just have to wait for it. PC is kind of heating up at the moment. Let's be patient with it. Whatever time it is, it's a valid time. So that's what it is for the moment. And once this thing is done, we will have the computed results. I can hear my fans kicking in my small MacBook for some reason. Maybe I just need to think of a couple of applications running one at a time. And then see, this is the longest one. It doesn't have any caching, it doesn't have any advanced features, it's just basically caching. So I would expect this one to take the longest. As you can see, it's still computing. Still, yeah, it's within this one here. If you want to take a look, right now it's executing this code here. This one here. I don't want to put the breakpoint because I want to get the time that I want. Perhaps let me put a breakpoint once it finishes calculating. Let me put the breakpoint. Which one is it? Once it finishes calculating. There you go. Let's finish calculating. So now let's just continue. See, it took a heck of a lot of seconds. So as you can see, this one took a fucking long ass time. It took 100 seconds. That's a lot of time. And this one took significantly less. And the bottom up, you can see there's a slight performance gain over there. Yeah, so I did say to you that, you know, if you manage to write the memo one, then you pretty much done. This is a little bit of an overkill. As you can see, the performance gain is it's fairly small. It is a performance gain after all. Let's see if we can run this again. Maybe let me just reduce my input size a little bit. And as you can see, they were all returning me the same answer. And well, I know that that is the correct answer. Let me reduce it to 750. Hopefully it won't take this much time. So let's give it another go. I see that was even way quicker, as you can see. For some reason, this time you see this took 59 milliseconds, and this one took a little bit more time over this one here. Which brings me back to the point that this is very beneficial if you have large data set. For a small data set, the memo is good enough. As that is reflected by this here. Let me just do it one more time. Let me just run it one more time and take a look. This is really fun stuff. You see, this time around it managed to be a little bit better. So that has a lot to do with your machine as well. There's a little bit of unknown variables that the computer does behind the scenes, which get also factored into our timings and whatnot. So as anybody has done a scientific experiment, you would know how a scientific experiment is done. You would have to do it multiple times and stuff like that. That's the same thing with the standard procedure here. So that's basically it. I will see you guys in the next one, and the next topic will probably be another dynamic programming topic. Let me know in the comments what you want it to be. Otherwise, smash the like button, subscribe to my channel. That makes me get interested in more topics, and let me know what is it that you guys wanna have next. Otherwise, that's me signing out. Cheers and have a good one. And stay fresh, always. I'm your host, I'm out.